Before we begin our discussion on geometric distributions, let's just do a quick warm-up. So say you roll a die 4 times. What is the probability that the first will be a 1 and all others will be something else? So remember, I'm rolling the dice 4 times. So I have a probability of success and I have a probability of failure. And these are nice examples because we can think about this logically. I have a 1 of 6 chance of rolling a 1, and I have a 5 in 6 chance of rolling something else. So if we consider this, we want the probability that the first one is a 1 and all others will be something else. So I want to be successful on my first roll and fail on the others. So I've got 1/6 times 5/6 to the power of 3, and that gives me 9.6%. So the probability that the first is a 1 and the rest is not is 9.6%. Next question, what is the probability of getting exactly 1, 1 and all others will be something else? So therefore we have exactly 1, 1, but it can be one of 4 rolls, right? So to have exactly 1, 1, that means there are 4 different locations that 1 could occur. I could have it in the first roll, I could have it in the second roll, the third roll, or the fourth roll. So I have all of these different opportunities to get exactly 1, 1. So I have 4 opportunities to have 1/6, and the rest of the opportunities are 5/6, or it's 4 choose 1 times 1/6 to the power of 1 times 5/6 to the power of 3, which gives me 38.6% chance. So now what of having exactly 1, 1 in 4 rolls? So now what is the probability that exactly 2 1s show up in 4 rolls? Well, if we think about using the approach that we used last time, we have exactly 2 1s, which is 4 choose 2, 1/6 to the power of 2, 5/6 to the power of 2. And when I do all those calculations, I get 11.57% chance of having exactly 2 1s. Next warm-up question. Determine a baseball player has a batting average of .320. Determine the theoretical probability that they could have a game in which they have no hits in 3 times at bat. So let's think about that. So our success is 0.32, or a P, our Q is 0.68, or a failure. So the probability that will have no hits in their first 3 times at bat would be the probability that X equals 0. So no hits for their first 3 times at bat, the probability of that is 31.4%. Determine the probability distribution for the number of hits per game. I'm not going to go through per game, we're just going to go through the probability distribution for those first 3 hits. So we have the probability of hitting 0 times, 1 time, 2 times, or 3 times in our first 3 at-bats. So we already have the probability of having 0 successes. So there's all our probabilities. We want to have the expected number. And so we're going to get our XPX. So the sum of our X times P of X, X being the number of hits, the probability of that is 0.959. And so we're going to figure out, we're going to use our expected value equation of e to the EX is NP. So you can see the sum of our probabilities is very similar to our expected value. Well, it's the same, 0.96, right? So we expect him to make, the expectation that he's going to make 0 through 3 hits in those first 3 is 96% because he's going to make 1 of them. Because he's at a 32% average or a 0.320 batting average, it means he's hitting about 1 in every 3 shots. So today we are talking about geometric distributions. Now, a geometric distribution, what makes it slightly different is that it considers wait time. And so here's our first example. that a simple game is played where the player must roll a 1 or a 6 on a die to win. Determine the probability for rolling a 1 or a 6 on the first, second, or third roll. So success is rolling a 1 or a 6, and so the probability of success, if you think about it, is a 1 or a 6. So we have two numbers possible. So we have 1 over 6 plus 1 over 6, or we have a 1/3 opportunity of being successful. And of course, we have a 2/3 probability of failure. So our probability of success starts with, we have a 1/3 probability of success on the first roll. Our probability, because remember, we're asking about the probability of our success on the first, second, or third roll. So if I am successful on the first roll, then I win. If I'm not successful on the first roll, I have failed. And then for me to be successful on the second roll, then I have that 1/3 chance of being successful. And then for me to be successful on the third roll, I have to have failed on the first two. For a 4 of 27 probability of being successful on my third roll. So this is, we could obviously have infinite rolls. And so this is called the sequence of Bernoulli trials. Instead of the number of successes, we're interested in the waiting time until the first success occurs. So rolling a 1 or a 6 immediately corresponds to a waiting time of 0. Rolling a 1 or a 6 on the third roll corresponds to a waiting time of 2 rolls. Okay, so it's the wait time. It's not when you've won, it's how long you have to wait until you win. So characteristics of geometric distributions are very similar to binomial distribution. It's based on a series of trials. 2 possible outcomes, you have a success or a failure. The probabilities do not change from trial to trial, and the random variable is the wait time. So the number of unsuccessful independent trials before the first success occurs. So the formula for this is very similar to the binomial distribution. Not the same, but similar. So the probability in geometric distribution is given by the probability of x equaling x is 1 minus p, where p is the probability of success, times to the power of x, times p to the power of 1. Right? So p is the probability of success, x is the number of failures before a success. And so the expected value of a geometric distribution is given by or basically, it is just the probability of failure divided by the probability of success. Let's put this again into action. So we're going to toss a fair coin repeatedly until it comes up heads. What's the probability that the first head occurs on the 5th toss? So remember, think, if I'm having it on the 5th toss, that means that I have had 4 failures before I get a win. So we have the probability of having a win on the 5th toss is a 1/2 to the power of 4 for my first 4 losses, times the probability of winning, which is 1/2. Because we're tossing a coin, the probability of winning and losing is the same, and so therefore this is basically just 1/2 to the power of 5. So the probability that the first head occurs on the 5th toss is 1 in 32. Next example, a computer generates random numbers from 1 to 25. What is the probability that the number 10 will not appear until the 6th number? So our number of successes is 1 in 25 because we're only looking for number 10. And we are having, so if it's not going to appear till the 6th number, that means I'm going to have 5 failures and the probability of it not being number 10 is 24 of 25. So here's how we set that up. I have to have 5 failures, so I have to have 24 out of 25 possibilities happen 5 times before I win, and my chance of winning is 1 in 25. And so therefore, the total of all of these, when I multiply these all together, is 3.3%. So what is the expected number of trials until 10 appears? Remember, that's the probability of failure over the probability of success. Or I would expect to have 24 trials before I have success, because I'm only having a 1 in 25 chance of success. So the expected value, so I'd have to generate 24 numbers before I would generate a 10. So this next example, there's some double negatives. So Steve scores on 80% of the penalty shots that he takes, which means that he only misses 20% of the time. So what is the probability that he does not miss in his first 5 shots? So this is just asking what is the probability that he is successful in his first 5 shots. So therefore, the probability of him scoring on the first 5 shots in a row is about 33%. So now what is the expected value of that? So remember, expected value is the probability of failure over the probability of success. Well, success in this case would be him missing the shot, right? Because it's asking what if he does not miss in the first 5 shots? So not missing is the success. So his expected number of shots that he will not miss is 4, which makes sense because 4 of 5 is 80%. So last example, on average, a soccer goalie saves 9 out of every 12 shots. What is the probability that the first goal scored occurs on the 3rd shot or later? Now, because he has he saves 9 out of 10 shots. So that means that only 3 out of 12 shots go in. And a success is when he fails to save the shot. So success in this case is him missing having the goal go in. So there's only a 3 in 12 probability that happens. So in this case, failure is him saving the goal or have them not scoring. So if it's the 3rd shot or later, and there's 12 shots taken, we want to know what is the probability of him, the first goal being scored, the 3rd shot or later. So remember, this is or later, so this is the probability of having to wait at least 2 shots on goal for a goal to occur. So here's one of those times when it's going to be a lot easier to use the indirect method rather than add up 2, 3, 4, 5, all those probabilities. Let's subtract all those from 1 minus. So it'll be 1 minus the probability of no shots minus the probability of 1 shot. So here's how we set that up. So we have a 9/16 probability that the first goal scored occurs on the 3rd shot or later. So we're saying that there is a 56% probability that a goal will be scored on the 3rd shot or later, which makes sense because he only saves 9 out of every 12 shots.